It should come as no surprise to you that the rates of reactions are very temperature dependent. If you imagine an ice cube melting on a hot day versus an ice cube melting, say on a cool fall day, obviously those are going to melt at very different temperatures. Now, Savante Arrhenius, which as a side note is probably the coolest name in chemistry, figured out a way to write an equation that would describe the temperature dependence of a reaction if you knew a couple of variables. The equation is shown here, and we call it the Arrhenius equation. In this equation, K is the rate constant, A is what we call the pre-exponential factor. It's a constant that's the same at all temperatures, but it's unique for each reaction. E sub A is the activation energy, or the energy required to get to the transition state from the reactants. R is the ideal gas constant, and T is the temperature in Kelvin. We can represent the activation energy graphically here. I've done this one for free energy, but you could use internal energy as well. And the difference between the change in state function, which depends on the reactants and products, in this case I've used delta G, but this could be delta H, delta E, whatever. All of these state functions only look at the difference between reactants and products. Activation energy, on the other hand, is the difference in energy between the transition state energy up here, which we'll write out here, transition state, and the reactants. That's how much energy is required for that molecule to make it over the energetic barrier and become products. On its own, the Arrhenius equation is not particularly useful. And the reason for that is that it's hard to predict the pre-exponential factor A. However, if we take two Arrhenius equations at two different temperatures for the same reaction, and we divide them by each other, the pre-exponential factors cancel out, and you can rearrange it into this equation here, where now we have no pre-exponential factor, and we can simply relate the two rates at two different temperatures to the activation energy. This equation is very useful if you want to find the activation energy, because you can simply measure the rates at two different temperatures. On the other hand, if you know the activation energy, this equation will allow you to predict the effects of temperature on a given reaction.